Yes, so we are back with our problem which I gave yesterday. This was the problem, and this is an Atwood machine. How do we proceed? What are our coordinates? Let us say that this distance, is a very good practice to locate your center of mass, and the generalized coordinates being used for that helps. So this is x1. Let us say that this one is x2. So basically this is the center of mass of M2, and let us say that this is the origin, this being the reference level, because we have to compute potential energies, right? And now the string is inextensible, and the pulley has no mass, idealized condition, the simple problem of Atwood you got in Newton. And so the potential energy in this level is 0. V0 initial is 0. So this is what I mean. Now if the string is inextensible, it is obvious that x1 plus x2 is some constant L. So what do we get from this? Let us express one of the coordinates in terms of L and the other one. Like I'm going for x2 as L minus x1. Now from this one, we are going to use this in our Lagrange. And what is x2 dot? Minus x1 dot. We are also going to use this stuff in our Lagrange. Now we are going to proceed with finding T. What is the kinetic energy of this system? Is it visible? Sorry. Yeah, what is the kinetic energy of this system? Yes, it is half m1 x1 dot squared plus half m2 x2 dot squared. x1 dot squared is the velocity square along x1 direction, x2 dot squared is the velocity square along x2 direction. For individual rigid bodies, the individual translational kinetic energies are computed and written. And what is our potential energy for this system? Give it a thought. But before that, let me simplify this kinetic energy term by expressing x2 dot in terms of x1 dot. So you're basically getting something like half m1 plus m2 x1 dot squared, because this x2 dot squared is minus x1 dot squared, that is x1 dot squared, and this is the final expression of kinetic energy of our system, right? Yeah, so now I will rub it off and write the expression for potential energy. Give it a think, what can be the potential energy of our system with this one as our reference level. This is our reference level. Give it a think while I'm rubbing it off. Yeah, so I think you have got the expression for potential energy. It is basically the V, it's visible, yeah, that's equal to minus m1 gx1 minus m2 gx2. That minus comes from the sign convention. Now if I express x2 in terms of x1, I get minus m1 g x1 minus m2 g, what is x2? L minus x1. If you simplify this, you are getting x1 g m2 minus m1 minus m2 g L. And what is our T? Sorry, what is our T? We remember what is L. L is T minus V. Now in this problem I am going to solve the Lagrange equation using L. I'm not going to use the previous method of doing the partial derivatives in terms of T's and V's. So we are not using that 1, 2, 3 and 4 method. The method is same. We are simply doing stuff in terms of L directly, and this is how we will do this problem, a bit different, but the result is same. So this is L is T minus V, and that simplifies or boils down to, I think, will it be visible? Yeah, that's basically half, if you remember, T m1 plus m2 Yeah, m1 plus m2 x1 dot squared plus m1 minus m2. Notice here I've changed the signs. gx1 plus m2gl. This minus was made plus by taking this minus common and making m2 minus m1 as m1 minus m2, and this minus becomes plus in doing this subtraction. This is the Lagrange over here. This is our Lagrange. This is the Lagrange. Okay, now first we have to compute. So I'm keeping the Lagrange intact and just rubbing off this upper expressions. So the first piece we are going to get is basically, yeah, the first piece is partial of L with respect to partial of x1. Remember, all our equations are in terms of x1. So basically that is partial of L with respect to x1. I'm getting m1 minus m2g. Simple. Because L here will be partial with respect to x1, and if you find any term with x2, just 0. It is ruled out simply. And the next piece is partial of L with respect to partial of x1 dot, and derivative of that. What's this? This is also simple. Summation of masses times x1 double dot. Because there is a d by dt, I directly wrote this. Partial of L with respect to partial of x1 dot is m1 plus m2 x1 dot, and derivative of that with respect to time, that is this quantity. This is the piece you get. And what do we know from Euler-Lagrange? Now you might have noticed that in our Atwood machine, was there any kind of non-conservative forces acting in this system? No. So our RHS is 0, which means this expression is equal to this expression, if you remember from my video 1 on Lagrangian formalism. So by doing that, we get the final equation of motion, which turns out to be, I'm saying that d by dt of partial of L with respect to partial of x1, this is partial of L with respect to x1, and by that I mean x1 double dot is m1 minus m2 by m1 plus m2 times g, and this is what you had anticipated or could foresee from Newton's laws. Basically, this is the working process of Lagrange. This is the final equation of motion of our Atwood machine system, and this term is the acceleration along a1 that one x1 direction, and basically this is the difference over sum by times g, the gravitational acceleration, and this is the simple equation you get. Thank you for this, and I hope that in the next video the problem which I'll take up will be very complicated and advanced, and that problem needs a separate video because of the length of the problem. As of now, thank you. Hope you enjoyed.